The next step in what we're going to be going over today is finding a vector from its components. And we're going to talk a little bit about what the components are and what we can do with them, and then how to solve some equations with those components. So right here, the first part that you're going to talk about is what exactly the components are. And what they are is the direction, and we have a two-dimensional XY chart, right? So they are the two directions that are going to give you the resulting coordinate of that vector. So here we have a 3-meter x direction and a 4-meter y direction. And what that gives us is our endpoint, which is really just the xy coordinate. So 3, 4, that's our xy coordinate. So that's our endpoint. That's where the vector ends at. That's the components that added up. So what do we do with those? Well, if you look at the way that it looks with those two components, is it looks like a right triangle. So if we isolate the x component and the y component, we pretty much have two sides. And what we can do with two sides, as you guys remember, is find this angle here, or the hypotenuse, which in this case would indicate what the magnitude is of the resulting vector. So underneath here on the side, you can see that they have the math on how they get this, and we'll kind of go through that a little bit, and you guys will get a chance and see some samples of it later. But just to take us through the reading, you can see that obviously we have an adjacent and an opposite side here. So we know that we should be using tangent. And what we can get from that is an angle, which is going to be the first step in finding our direction. Now, as far as finding the magnitude of that vector, well, that's going to be a hypotenuse, and we can use our Pythagorean theorem. So a squared plus b squared equals c squared reminds us that 3 squared in this case and 4 squared will equal c squared, which is going to be the hypotenuse. So they input those here. They have 3 squared, 4 squared, and then they have the square root of those as your method of finding the resulting vector magnitude. So 5 is the magnitude. So we have a magnitude of 5 and a direction of 53.1 degrees. So this is what we need to call that a vector. 1 by itself, just 5, that's just a scalar. And 53.1 degrees, that's just an angle. But the two of them together create a vector. So if we're asking to find the resulting vector, or we're using vectors to find a value when we're doing our AC trig, or if we're doing any rigging assignments and engineering a lift, this is the information we're going to call a vector. If you're just looking for the magnitude, you're just looking for one number. If you're looking for the angle, you're looking for another, but the vector itself is a combination of the two. So here they have us solving another one, and the first thing you're going to notice in this example is that the vector itself is in a different quadrant than we had before. So when you're in the first quadrant and you have two positive values, you're going to have your angle right here, and this x horizontal line is our starting point, so that's 0. So when you have this angle, that's your answer, and that's it, you're done. But when you're in any other quadrant, there's a couple of rules we're going to talk about that you need to remember. And the answer that you get on your angle, you're going to realize it may not be your overall direction. So when I talk about direction, I have 360 potential degree directions that this vector could be going in. And the methods that we're using to solve for the angle when we use our right triangle is never going to be greater than 90 degrees. These angles can never be greater than 90. They can get really close, but they can't exceed 90. So when you solve for the angle, you need to know what you're going to do with that piece of information. And knowing that the x is your origin is technically 0 degrees. When you draw your little chart and see where your vector is, and you create your imaginary right triangle with that, you need to know what this degree tells you in the grand scheme of really solving for this. Because you could have also made your right triangle off that same vector and use this information and been finding this angle here. So what you do with that, you're going to need, once you get that angle, you're going to need to look at the big picture here. So in this case, we'll just look at the math that they did and kind of walk through how they got there. So they have 115 kilometers east, which is a negative x in this direction on this chart, and 175 kilometers north, or y, our positive y direction. And that those two together give us our resulting vector. So in this case over here, we have two sides of a right triangle, 115 and 175. And again, when they're going to use tangent, you're pretty much always going to be using tangent when you have these values. And they came up with 56.7 degrees. So let's just write that in there like we solved it, 56.7 degrees. Now what you don't want to do is say that this is my answer for my direction. Once I find the magnitude, I just write that next to it here and call that good. This would be wrong. And why that's wrong is because at 56 degrees, that could be anywhere. That doesn't really tell me anything, because that 56 degrees could be here, could be 56 degrees in this direction, and that could be it here, it could be this direction if this was your right triangle. And that doesn't really give me a reference point. My reference point is I must calculate it from 0 out of a potential of 360 degrees. So in this case, you can see that we've already passed 90 degrees here, and then we keep going before we hit that vector. So that's going to be much more than 56.7 degrees. And we'll look at the math on how they get it, and then I'll show you a couple other techniques if you just want to use the common sense method, or you want to do the mathematical calculations on it. That'll be up to you guys, but we'll be doing a lot of these sample problems to kind of get some practice in it. So from the positive x to the negative x line, we have 180 degrees here. And you're in this category over here, you're in this quadrant. So you have 180 degrees you're dealing with, that's the total. 180 degrees in that range from the x horizon on the negative and positive x. So they give you 180, and you're going to subtract what that angle is, which was 56.7. Now what's left is our actual direction, because it's going from the 0 all the way to here, and that's going to be the difference of our actual angle. Because the total is 180, we're getting rid of the value that we calculated and calling the actual direction itself 123.3 degrees. So if that doesn't make sense and you wanted to look at it from a different perspective, I probably would have solved this triangle a little bit differently here. I would have had this be my right triangle, and then I would have said, okay, I got 175 on this side of that, and 115 on this side. And if I calculate my angle here, I'm going to get the difference of 56.7. So if I calculate my tangent from that perspective, if this was my angle, these two values over here, the 175 and 115, they would have flip-flopped, because now I'm looking at the opposite over the adjacent from a different perspective. When this A angle was our perspective, the opposite was 175 and the adjacent was 115. Now we're doing a different triangle in a different direction. And from this new angle I would have calculated it from, it would have actually been, the opposite would have been 115 and the adjacent would have been 175. And one thing you'll notice about doing it that way is that in this angle, they got 56.7. If I had input tangent 115 over 175, I would have gotten 33.3 degrees. Now if you add those two up, you should get 90, right? The overall 90 degrees. And if I knew that my 33.3 degrees here ended at this y line, and that what was left over was 90 degrees, I could just add the 90 and gotten 123.3 degrees. So there's a couple ways to calculate this. Their way is a little bit cleaner if you like doing math. The other option is a little bit cleaner if you just like to kind of visualize it, and you can see that we have one quadrant it has to pass through, and then we meet the actual side. You add that vector into there and that angle. So you add that angle into there, and you get the 90 up to this point plus the angle you got. And when we added those two together down here, we got our resulting direction. So again, we'll look at how they did it. They calculated the two coordinates as the sides of a right triangle using tangent, their opposite over their adjacent, and what they got was 56.7 degrees. They subtracted that from 180 and got their direction, which was 123.3. And then when they did the Pythagorean theorem down here, 115 squared plus 175 squared, you take the square root of that, they got their 209. So the resulting vector is 209 kilometers at 123.3 degrees. Now the other example we scrolled past up here kind of shows what I was talking about in a different quadrant. So if you had this resulting vector down here, and you calculated A, with this being your right triangle that you drew in there, you're going to be looking at an overall spectrum of 360 degrees. And you can see over here in their math, when they got their angle, 360 degrees, they subtracted their angle from that. And their resulting direction was 324. And you can kind of see how they got 324, almost 360. It's just shy of it because it travels through 90, through another 90, through 270, and then partially to the 360, coming up with a total of 324.5 degrees. As far as finding their magnitude, again, that's just the Pythagorean theorem hypotenuse of this 7 and 5, which you can see here, 7 and 5. So in this example, their resulting vector was 8.6 miles at 324.5 degrees. So those are a couple quick samples. We'll do some more drawn out ones later, and you can see some more in the book here. And the last thing I want to cover before we go on to some practice is we have the glossary and formulas here, which are an excellent bank for test questions and some very important stuff to know to understand what we're talking about when we use these videos. If you don't understand the vocabulary we're using, describing the number plane or displacement or components, go ahead and take a look at this, and don't start solving too many of them or getting too deep into the reading until you understand this. So some of the important ones, like we talked about, displacement, the components of a vector, what is that? So the coordinates, right? The number plane, you got resulting vector, so that's going to be when you have a sum of two vectors, right? And then what the difference between a vector and a scalar is. Standard position, talks a little bit about that. The vectors, just the definition of vector, and then the x and y components. Understand all these terms are before you start getting too deep into these, or you're just going to get lost real quick. And as far as the formulas go, they have them all kind of organized in one place for you here. If you don't understand why they're using any of these or where they get them from, it might be good to go back up and read the chapter over again. The values they're putting in here, like for example this is just a derivative of this. So when you see them using the fancy r of x squared, they're just calling that a side of a right triangle. So don't get too mixed up by that. Okay, that's all I got on this chapter, so go ahead and start working on some of the solutions for the vector problems we're going to assign, and let us know if you have any questions.